Good afternoon, everyone, and welcome to today's webinar, The Ins and Outs of Using Dynamic Regression Models for Forecasting. My name is Eric Stellwagen, and I will be the moderator today. Let's start by quickly walking through a few logistics. The webinar will run approximately 45 to 50 minutes. As always, we'll save some time at the end for Q&A. During the webinar, you can submit questions using the control panel on your screen at any time. I will monitor these questions throughout the webinar and will compile a list for the Q&A at the end. We will also take any questions submitted during the Q&A session itself. We'll try to address as many of your questions as possible, but if we don't get to your question, you will receive a follow-up email after the conclusion of the webinar. We are taping this webinar and will email you a link to the video sometime next week. This video will be posted to our website and YouTube channel, where you can find a full archive of past webinars. They are all free and a great way to catch up on any past webinars that you may have missed. So without further ado, let me turn it over to Eric Stellwagen and Sarah Darin to present the webinar, The Ins and Outs of Using Dynamic Regression Models for Forecasting.
Okay, well, thank you, Eric. I'm Eric Stellwagen. I am the president and the CEO, as the slide says, of Business Forecast Systems, the creators of Forecast Pro. Okay, and I've been told we're having a slight technical difficulty here, so let's make sure that you can see my screen. Okay, so this is probably a little more interesting at this point, since you can see. So again, my name is Eric, and I'll be one of the presenters today. I've basically spent my entire professional career in forecasting. I've been doing it for, as the slide says, for over 33 years. And I have also, during that time, worked with a lot of different companies and have gained some insight into how organizations approach the forecasting process. And that's been very useful, as forecasting really is kind of a combination of knowledge about forecasting and how to use methods, along with empirical knowledge of what works and how to solve practical problems within an organization. With me today is Sarah Darin, and I'll let her introduce herself.
So I'm Sarah Darin. I'm a senior consultant here at BFS. I've been here for a couple years now, but I actually have, it's really over 20 years of experience in statistical consulting, business forecasting, and marketing analytics. So like Eric, my entire career. Most of my career actually has been really focused on regression in terms of an analytics technique, both for forecasting as well as really, I was doing a lot of marketing mix modeling out of Nielsen before coming here. So regression analysis is something that I'm very familiar with, and happy that it's the topic of today's webinar.
Yeah. Okay, so here's a roadmap of how we're going to spend the next hour or so. We're going to start pretty general, talk a little bit about the pros and cons of regression modeling. The majority of the webinar will actually be spent running examples of how to build and diagnose dynamic regression models. As Eric Stellwagen mentioned, we'll leave some time at the end for questions and answers. And again, if you do have questions that occur to you during the course of the webinar, feel free to use the chat facility to pose them. So let's start with some pros and cons. A lot of business forecasting is done using what I call time series methods. And by that I mean methods that base the forecast solely on the past history. So methods like exponential smoothing and Box-Jenkins are usually applied as time series methods, and they're good at pulling things like trends and seasonal patterns and projecting them forward. Regression is a bit of a different animal. It allows for the introduction of explanatory variables. So in addition to using the past history, we're looking at relationships between what we're trying to forecast, for example, sales, and explanatory variables, which could be things like prices, measures of the economy, promotional schedules, etc. Okay, so it's a model that not only generates a forecast, but also can give you insights into relationships between variables. And that's very useful and important. So for example, if I build a well-specified regression model and it includes price, what that is going to allow me to do is not just generate a forecast for my sales, but it's also going to help me to understand the relationship between my sales and the price. And that could be very useful in its own right. So I could use that information to, for example, set pricing policy. So that's pretty good stuff. Regression also allows for what some people call what if. You know, what if we raise the price? How would that change demand? What if we lower the price? What if we keep it the same? So again, in regression, by varying the scenarios for the explanatory variables, we can see what kind of impact they have on the forecasts. Dynamic regression can also exploit what's called leading indicators. Now we're going to talk a bit about variables and different types of variables, but one of the key things about using variables in regression is the question of when does the impact occur? And we tend to think in terms of what you could call concurrent relationships. So that would be, let's go back to our example of sales and price. If I change the price this month, there's a question of when does it change the demand. If it's concurrent, then it's immediate. So I change the price this month, that changes demand this month. Okay. On the other hand, some things are not immediate. For example, let's say that I'm in the business of manufacturing doors. Okay. So, you know, doors that are going to be used when we build houses, you're going to need some doors. Very often, if you're forecasting building materials, an explanatory variable that you might want to keep an eye on is housing starts. Okay, so somebody who's going to build a house, the first thing they have to do is to take out a permit, and the record of how many permits have been issued is called housing starts. If I'm in a company that's manufacturing doors, I can watch housing starts, and I know that if housing starts show a big increase, that's going to lead to an increase in demand for my products, for the doors. But it's not going to be concurrent, because the first thing you do when you take out a building permit is not to buy the doors. You need to excavate the site, you need to lay a foundation, you need to do the framing, and it's probably a good 6 months before you actually order the doors. This is ideal for regression. This is what's called a leading indicator, because a change in the permits issued leads to a change in demand for my products, but not for 6 months. And what that means is that I have this 6-month window where I'm relating my sales to something that's already happened. So if the indicator is concurrent, I'm going to need a scenario for the future. But if it's a leading indicator, then I don't for the number of periods that it leads. And that's great. So if you have leading indicators, you definitely want to consider using regression. Now, what's some of the downsides here? Regression does require a bit of work. So it's not a fully automated technique, although there have been some strides made in that direction recently, and we'll show you that. It requires a bit of knowledge about how the models are built and how to diagnose them. And it also often requires a bit of experimentation. Okay, so we'll see this, and again, as I mentioned, a large part of this webinar will be in the form of a demonstration. This next bullet here is the big one, okay? And I'm going to read it, and then I'm going to go back and sort of explain what it means. So, even if the regression model is good, meaning that even if I build a model, I put in these explanatory variables, and it truly captures the relationships between variables, difficulty in forecasting the explanatory variables will result in poor forecasts of the dependent variable. So what we're saying here is, for example, I build a model that is forecasting demand for my product, and it includes, say, interest rates, okay? And it's a good model. It really does explain the relationship between interest rates and sales. And when interest rates change, it really has an impact on my sales, and the model gets all that. The downside is that if this is concurrent, a concurrent relationship, then in order to use this model for forecasting, I have to put in a scenario for what the interest rates will be in the forecast period. Put another way, I have to forecast interest rates before I can forecast my sales. It may be harder to forecast interest rates than to actually forecast my sales. And if I don't do a good job forecasting interest rates, I'm going to have poor forecasts of my sales. So this is really the downside, which is, again, it's not enough to just know there's a relationship. If it's concurrent, you need to be able to come up with a good scenario for the future of the explanatory variables. Finally, regression does require data. And the more data we have, the better off we are, and the better we can really understand the relationships between variables. So Sarah will talk a little bit more about data length when she starts talking about variables. Okay, now we're going to just very quickly kind of get across what's called the classical regression model. And this is sort of the basis for all the dynamic regression models. And the basic idea is you have a variable you're trying to forecast, in this case, sales. You are going to, we sometimes will call that variable to be forecasted the dependent variable. You are relating sales, in this case, to another variable. In our example, advertising. Advertising is called an independent variable or an explanatory variable. The relationship between sales and advertising is quantified using what's called a regression coefficient, which here we have symbolized using a B. But let's think about this for a second. If we increase advertising, let's say that we increase the advertising budget by $1, then according to this equation, sales will go up by B. So if the coefficient B was 1.3, it says for every dollar we spend in advertising, we're getting back $1.30 in sales. So that would be great. Then that would be pour some money into advertising if that was the case. Now, what about the rest of this equation? There's a constant term. This is just a number. Some people call it an intercept. But the idea is, what if your independent variables, advertising in this example, were 0? What would we sell? So if we have a month where we don't spend any money on advertising, we're still going to sell something, and the constant term lets us know what that is. Okay. Finally, we have the part that we're not explaining by the model, which is the error. Now, in a textbook, this would probably be symbolized as it is in this red version of the equation, where the y is the dependent variable. There's a little subscript t here to say it's a time series. The x would be the explanatory variable, advertising in our example. The regression coefficient b, a constant term, and we use an epsilon for the error. So just in terms of terminology, we have the dependent variable, we have the independent or explanatory variable, and often this is more than one, so we have explanatory variables. We have regression coefficients, we have a constant term, and we've got an error. And this again is sort of the basics of our regression modeling. So we'll see when we start to talk about dynamics that this is a framework which can be extended, but this is where it all begins. Okay, with that, I'm going to turn the presentation over to Sarah, and she's going to talk a little bit about variables.
So one of the things that we want to think about when we're building a regression model is the types of variables we should be looking at. The variable selection process is really, it's one of the most challenging and time-consuming parts of a regression analysis. The first step is typically going to be to ask yourself, what are my key sales driver and what data or variables do I have to capture them? For forecasting, it's actually really important to focus on the handful of really important sales drivers, the ones that really move the needle, so that if you're looking at it graphically, you can visually see an impact of a potential explanatory variable on your sales variable. So if the explanatory variable is going up or down, you see the sales variable going up or down as well during the same time period. It's also helpful to think about variables as you do the collection process according to the two categories that we're showing here. So internal variables and external variables. Internal variables, these are kind of the easier ones because these are the ones that you can control, that you're planning for. So things like price, promotion, advertising, something like the number of sales reps that you have in a territory. So any of those things that you're doing to help your company drive sales are the types of internal variables that you might want to think about when you're collecting data. In contrast, there are also external variables. Now, these are the ones that could potentially have a very big impact on your sales, but you don't have control over them. So this might include things like weather, the economy, competition, or demographic trends. So as Eric was talking about, another important thing to think about with variables is the fact that you need to provide a forecast for all of these variables. This is actually pretty straightforward with internal variables. You typically are going to plan for prices again or plan for promotions. So what happens is typically going to be what you planned to happen. For external variables, that is a lot more challenging. So if you do have a leading indicator, you're in much better shape. Again, going back to Eric's example, if housing starts 6 months ago is a leading indicator in your model, you're pretty much set for the first 6 months that you're forecasting out. If it's concurrent, it can be a lot more challenging, and a lot of the variables, the example external variables we're showing here, are definitely challenging to forecast. That said, this is one of the places where some of the what-if analysis can come in handy. So what's commonly done for these things that are a little bit more difficult to forecast is to look at, say, what if the economy is in a boom period. So looking at a forecast of your sales with a very optimistic economic outlook. And then in contrast, looking at what your sales would be if the economy is slowing down, so a pessimistic economic outlook. So even though these things can be a little challenging to forecast, you do have the ability to look at ranges of possibilities for these external variables. So another thing that you're going to want to think about when you're gathering your variables and selecting them for your model is how many variables you should be using in the model. So we started out talking about how we really want to be identifying our key sales driver. The idea here is that when you're building a business forecasting model, the more variables you're putting in the model, the more unstable your model is going to become, and often the less accurate your forecasts will become. So in order to provide reasonable forecasts, you really want to be thinking about putting in a reasonable number of variables. From a statistical standpoint, a commonly used rule of thumb here is that you want to have at least 10 data points for each variable in your model. That's not like a written rule, and there's certainly some wiggle room around that. But to give you some context as to what I mean by that, suppose you have 5 years of monthly data. You would then have 60 data points, so 12 times 5. If you were building a regression model with that data, you really would ideally not have more than about 6 variables in your model. If you went up a little bit above that, that would be fine. If you were going to like 15, chances are that's not going to be a good model. So at this point, we're going to take a look at an example. And what, first of all, the product that we're using here is Forecast Pro Track. And this is actually a version that we'll be releasing in the next few weeks. So we have 5.1 coming out for Track. At the same time, we will be releasing Unlimited 10.1, as well as a new product for us called Forecast Pro 100. Forecast Pro 100 is going to be replacing our Forecast Pro XE product. And, you know, XE users out there will be getting an email shortly about how they might be able to upgrade to Forecast Pro 100. But the key thing in all three of these products is that all three of these products will be offering dynamic regression and the functionality that you're going to be seeing today. So that said, let's put more focus on the graph that we're looking at here. And whenever we begin any forecasting project, one of the most important things to do first is actually to visually examine your data. So that's what we're going to start out doing here. What we're looking at here is about 8 or 9 years of monthly electricity sales. So if we look at the data here, it looks very regular. But what's really striking is these peaks that you see happening here, and they're happening pretty consistently right in the summer period. The peak is typically right in August. And if you think about your electric bills, that's also the peak of your electric bill. And the reason for that is probably pretty clear. When it's hot outside, like it is in August, we turn on our air conditioning and our electricity usage and our electricity bills skyrocket. It's also worth noting that how high the amplitude of these summer spikes is really quite variable across years. The most striking thing is this August 2015 is really high, and then the following year there's a significant drop. So while there's clearly seasonality going on here, the amplitude of these spikes is really being impacted by how hot each individual summer is. So this August 2015, a lot more usage, likely a whole hotter than the 2016 data here. Also worth noting is these winter spikes here. So this is actually electric usage in the greater DC area. So in DC, there's a good amount of electric heat there, and that means that when it gets cold in the winter, people are going to turn on their electric heat, and we see another smaller but still very noticeable spike in those winter months. So that's a quick look at our data, and before we really start building the regression model in any great detail, a good practice when you're building a regression or really doing any type of modeling is to come up with a good baseline that you're looking to improve on. So for this particular series, a good baseline model is going to be just pure time series analysis. And the idea here is, as Eric was saying, time series is actually pretty uncomplicated and straightforward. Regression, on the other hand, can be time-consuming and can be a lot harder to maintain. So we really only want to be moving in the direction of using a regression model if there's significant improvement over that simpler time series benchmark model. So I am going to add in the forecast and open up the forecast report here. And by default, when we're not applying a model directly, we're using expert selections. What we're looking at is the expert selection model down here, which is an additive winters model. And up on the graph here, you can see that I added in the red fitted values during the historic time period, and then we can also see the forecast over here. From a visual standpoint, when we look at this graph, the way we want to assess the fit of the model is to see how closely the actuals, the red line here and the green line, track each other. And the answer to that is, it's doing a pretty good job. But then as we get to the peaks here, we can see that while the additive winters model is capturing the general patterns in the data, it's really missing some of these seasonal peaks. So when it's really hot during the summer, the exponential smoothing isn't necessarily able to capture the size of the peaks. And if you think about how exponential smoothing works, that makes sense. Exponential smoothing is really looking at what has happened in prior years as a way of figuring out what is going to happen this year. So you can see in this first high year here, what was predicted is pretty similar to what happened last year. Exponential smoothing is adaptive, so as we move here, the peaks get a little bit higher as we have this series of hot summers, but still under predicting for all of them. And by the time we get to this very hottest summer, it's still way under, and then in the next year, we're way over because this summer was cooler, and the exponential smoothing model is unable to reflect that. So this is data that we can look at and think temperature, concurrent temperature is actually really important, and probably we're able to really improve our forecasting model by understanding the impact of variables like that. So let's take a look a little bit at the first step of the regression building process. And actually, before we do that, in terms of the baselining, one of the things that we're going to want to be able to do is compare some of the quantitative goodness of fit measures for our baseline model to our regression model. So what we have down here is we have an adjusted R-squared of 0.89, and that means that our additive Winters model is explaining about 89% of the variability in historic electric sales, and we have a MAPE of 5.9%. So those are just two numbers we're going to make a note of and compare to some of the regression models we start looking at as we do the regression building process. So really, the first thing that we want to do, just like we visually examined our dependent variable, we want to take a look at what our explanatory variables look like. And let's actually start out by defining what they are. So we have AC saturation, and that's simply the percent of households with air conditioning. We have cooling 66. Cooling 66 is a variable that reflects within each month the number of days that it's the average daily temperature is above 66, as well as how far above 66 it is. We have cooling 76, which is similar to 66, except with 76 as the critical value, disposable income, and then heating 55. So this is similar to the cooling variables, except it's designed to measure when it gets cold. So it's looking at the number of days in a month where the average temperature is below 55, and then also reflecting how far below 55 it is. So that's what the explanatory variables look like independently. But what we really want to do is understand if when these explanatory variables are moving up or down, if we see movement in the sales as well. So I am going to turn off this here. Let's start off by looking at sales alongside cooling 66. So on the top here, we now have, close that bottom here. On the top, we now have the sales in blue now. And on the bottom, we have cooling 66. And what you can see is that there's definitely a good alignment between our explanatory variable down here and our sales variable, electricity sales on top here. So when we look at this visually, it certainly makes sense that cooling 66 is going to be a potentially a good variable in a regression model. Also worth noting over here that we have actually provided forecasts for cooling 66 within the data that we read into Forecast Pro. These are based on basically what's normal for for this variable. So I believe that it's based on maybe, like, I don't know the number of years, but it's based on averages from prior years, and that's kind of best practice in the industry to do things based on normal temperatures. So at this point, we're definitely thinking that cooling 66 is a good variable to be considering. And let's take a look at some of the other ones here. So we also have cooling 76, which is similar. The spikes in cooling 76 are a little bit smaller, but you can also see that there's a little bit more variability. So these really high peaks here do seem to be reflected by higher peaks relative to some of the other ones in the past for cooling 76. One of the reasons that we might want to consider including both 66 and 76 in the model is that the impact on electric usage when you go from, for example, 80 to 85 might be very different from what the impact is when you go from 70 to 75. And that actually, without giving away our regression model already, that actually does turn out to be the case, that the impact of going of temperature increases in that higher range has a bigger impact on electric usage. So let's just look at one more variable here before we move on to the building process, and that's going to be this heating 55. So what we see here is our cooling variable is well aligned with these winter peaks. So again, this cooling 55 appears to be a good variable for helping to predict the timing and the amplitude of those winter peaks. Interestingly, it's even over here when you see this little kind of kink in the your explanatory variable, you're actually seeing that over here as well. So definitely you're seeing a pretty strong relationship there. And with that, I'm going to pass it back over to Eric to take us through the actual model identification process.
Okay, so just to summarize a little bit, we actually started off by building a exponential smoothing model for the data. As Sarah pointed out, we're using this as a baseline, and what we want to do is to use regression to try to improve upon these results. And one of the things she pointed out, which I'll notice again, is that one place where smoothing really doesn't do a great job is on these peaks. And so you can see like this big change between this particular year with the strong peak and a lower one. We're really not equipped to capture that using exponential smoothing. Okay, so again, these slides are really for your notes, but it's often useful to create a time series model for the dependent variable prior to embarking upon building a regression model. Again, it's quick, it's easy, it gives you a benchmark to try to outperform. Okay, now what's the work involved in regression? Well, Sarah mentioned this before, but probably the biggest chore is to collect all the independent variables that you think might be important, and if they're not leading indicators, to also figure out forecasts or scenarios for the future for them. After you have that, you need to build the model, and that's our next step here. So let's take a peek at that. So what I'm going to do is to go into regression, and I'm going to pull up this dialog box. And the way that it's implemented in Forecast Pro is that we have the terms that are available to include in the model here on the right-hand side. And in this box, we'll list the ones we want to include. Regression's available in a lot of other software packages in a very limited fashion. It's available in Excel, but not as dynamic regression. It's available in SAS and SPSS and eViews and a lot of other econometric software packages. For our example, we're going to start by really concentrating on explanatory variables. And so we've got a bunch of them. We've got the two different cooling degree day variables. We have the heating degree days. We've got the air conditioning saturation rates and the disposable income. So I've listed all of our independent variables here. And there's a question of which ones do I want to include? there's often there's kind of two approaches to regression. And one is where you include all the variables you think might be important, and then you build the model and you start eliminating variables that don't seem to be adding value. An alternative is to start with a very minimal model and just include the ones that you know to be important, and then to add additional variables one at a time to see if they're improve the model. The important thing is not so much which tack you choose to use, but a best practice is when building regression models, only make one change at a time. Now, I'm actually going to start with a model that includes the cooling degree 66 and the heating 55, and I'm going to turn off, by removing these check marks, the other variables. In Forecast Pro, there are two ways of building regression models. One is to determine your explanatory variables and to let Forecast Pro automatically determine the dynamics. This is new in Forecast Pro, and it works very well, and it's how we're going to start this example. So in this example, I'm just saying I want a model that's going to include my two temperature variables here, and I want Forecast Pro to automatically do the dynamics. And there it is. Okay, so I click the button and it builds a model. Now, notice a few things. This new model is fitting the data very well, and in particular, it's capturing the changes in these big peaks, including where they go from being quite high to dropping down. So by bringing in temperature right off the bat, visually, I can tell this is going to be a better model. Let's take a look at the model now. So here's the regression. It includes the cooling 66 and the heating 55. All of the other terms here are dynamics. These were put in automatically by Forecast Pro, and we'll talk about these in a little bit. But right now, let's concentrate on these heating and cooling variables. Each one has a coefficient. That was the B in our equation in the beginning of the webinar. Before you build a regression model, one of the things that you want to think about is what sign do I expect the coefficients to be? Should they be positive or negative? In this case, cooling degrees goes up, the variable goes up when it gets hotter than 66 degrees. And therefore, as it gets hotter, I expect to sell more electricity, and I expect that coefficient to be positive, and it is. So probably the first thing I look at when I build a regression model is, what is the sign of the coefficient, and is it what I expected? And if it's not, if this were a negative coefficient, I would know I have a problem. My model is saying that when it gets really hot, I don't sell as much electricity, and that does not make economic sense. So the first thing I look at is the sign of the coefficients. In this example, they're both positive, and since I sell more electricity when it gets hotter than 66 degrees Fahrenheit, and when it gets colder than 55 degrees Fahrenheit, this is what I expected. So far, so good. The next thing I look at is what's called the t-statistics. This is testing to see whether the coefficients are significantly different than 0. Obviously, if the coefficients were 0, we really wouldn't be adding much to the model by including the term. So the t-statistic really compares the size of the coefficient with what's called the standard error of estimation, but the error in estimating that coefficient. And if you divide these two, you get what's called a t-statistic, and you can look it up in a table to determine whether it's significant. If it's 0.999 or above for the percentile, it's saying it's highly significant. If you're used to significance levels as opposed to percentiles, the significance level would just be 1 minus the percentile. So a 0.01 significance level would be equivalent to a 0.99 percentile. Okay, but so far so good. Our coefficients are both the correct sign. They're both highly significant. Now, we had some other explanatory variables, and there's a question of whether we should try adding some. I might also mention in passing here, we already saw that this data fits the model better than our exponential smoothing, but our R-squared, which had been 89%, is now 99%. And the MAPE, which had been 5.9%, is now 2.75. So we see dramatic improvement in both in the within sample statistics. This is what's called a test battery, and these are what's called excluded variables. And they're testing to see whether variables you did not include in the model should come into play. Cooling 76 was one of the temperature variables we did not use in the model. The test is significant and it's highlighted in red. Air conditioning saturation rates and disposable income were also variables that we had but did not use. Those tests are not significant, and so they're not highlighted. And the program's also checking for things like the first lag of variables in the model and perhaps using a trend term. Bottom line is I look at this test and I notice that cooling 76 is highly significant, and that's evidence I may want to add it. So to add it, I'm going to click on it, and I'm just going to add it to the model using this menu, and that will rebuild the model, and it now includes that variable. The coefficient for our new variable is positive, which is what we expected. Everything's significant. The dynamics have been recalculated for the new model. That was done automatically by Forecast Pro. And this is now a very good model, and we're done. Okay? So if I use automatic dynamics, then really what I'm doing is just concentrating on the variable specification, the independent variables. And in this case, we had 5 of them to consider, and we ended up with the temperature variables and a very good forecast. It's forecasting, or at least fitting the data within a percentage point. So quite good. I'm going to go back to our slides for a second. And again, what was our work involved? Well, we had to collect these variables, including forecasts, and then we had to build the model. Now, the other part that we sort of allowed Forecast Pro to automate is the dynamics of the process. Dynamic models use the past history as well as explanatory variables to generate forecasts. And this can take different forms, but the common forms are using lags of the dependent variable. Put another way, doing things like what were sales last month or the month before, and can that help us forecast what next month's sales are going to be? And using really something called Cochrane-Orcutt models, which are using the errors and modeling them as a separate process. The Forecast Pro Statistical Reference Manual will go into greater detail about how these models work. Any forecasting textbook that includes dynamic regression or any econometrics textbook that includes forecasting will also describe these models. They're very mainstream models. But basically what you're doing is combining using the past history, much in the same way that exponential smoothing and Box-Jenkins do, with using explanatory variables. And that's sort of the definition of dynamic regression, is this addition of these dynamic terms. So back to our example. We had left off where we had done the dynamics automatically. And what I'm going to point out here is that's not the only way to do it. I could go back to my model settings, and I could turn off this automatic dynamics. And that would allow me to explicitly add any sort of dynamic terms I want to use. I'm just going to start with a model that includes a constant term, but no other dynamics, and build that model. I'm also now going to use what's called a bookmark to change my display to one that I prefer for regression. Here is our regression report. Okay, here's the graph that we were looking at previously. It's not as good as our last model because we haven't really nailed down the dynamics yet. And I've added something new, something called the error autocorrelation function. This is a diagnostic that looks for patterns in the errors. And ideally, I don't want this graph to be patterned. And I'd like for all of these bars to be non-significant, which is within those dotted lines. Here it's anything but. All of these are positive. There's a little bump here at 12, which is saying that errors 12 months apart from each other are particularly problematic. Another bump at 24 here. So if you're new to the error autocorrelation function, this probably doesn't mean much to you. But once you start to build these models and look at this diagnostic, there's a lot of information for people who know what they're looking at. So I look at this and I say there's a lot of patterns in the errors. There's definitely some seasonal patterning, and there's some strong short-term correlation as well. So I know that for those who are new to this, you're not immediately seeing all that, but it's here, and as you build these models and get used to it, it helps you to build these models quickly and to spot things. So I want to improve this model, and the question is how. I can look at our excluded variable tests and perhaps experiment with that. There's another test battery here that's for dynamics. And you can notice almost all these tests are red. And the program sort of looks through all this and says auto -1, which is a Cochrane-Orcutt model, is the place to start. Again, I know that there's a lot of short-term patterns here. This actually makes perfect sense. I'm going to add it to the model. And now the model's been updated. And you can see that that error autocorrelation function has changed a lot. A lot of that short-term pattern is gone, but that seasonal pattern is still there, 12 and 24 and 36. So there is a question of what's next. And again, it's now sort of an iterative process. I go back, I look at the sign of the coefficients. Those are correct. Everything's significant. So far, so good. I can look at dynamics or statistics like the Young box test and the error autocorrelation function. I can see there's some problems. I can look at test batteries and decide what kind of change to make. Here it says try adding auto 12. That's another Cochrane-Orcutt term. That will help me with the seasonal pattern. Again, makes perfect sense to me. I'll go ahead and do it. But what I'm trying to do is not to make you a regression expert in an hour. No one can do that. But what I'm trying to do is give you a flavor for how these models are built, both if we do automatic dynamics, which is very simple and straightforward, and if we do it interactively. And there it's a little more experimentation, trial and error, and using some of these diagnostics to help us along the way. So I'll stop the process here. I could continue and build an even better model, but you can see we're getting a pretty good model, and my purpose, again, is not to generate the best forecast for electricity demand in the greater DC area. It's to give you a flavor for how it's done, and I think I've done that. So I'm going to go back to our slides and just point out a few things that we've been doing. So the model identification process is really an iterative process. We start with the model. We look at how well it fits the data. We look at some statistics and diagnostics, and then we make a change. And that change might be adding or removing variables. It might be, if we're not using automatic dynamics, it might be experimenting with dynamics. And you continue the process until you're happy with the model, okay? Historically, automatic algorithms have not performed that well for dynamic regression. There are, for cross-sectional regression, there are things like all possible regressions and other approaches that do work reasonably well. But for dynamic regression, it's not been as successful as some of the others. But I think in particular with this automatic dynamic approach, we've really managed to streamline the model building process. So it's not fully automatic, but it's a whole lot easier than it used to be. So the next thing that we've been doing as part of our example is what you might call diagnosing the model or validating the model. You want the model, this is the bullets here tell us what to look for. We want the model to make economic sense. And by that I mean we want the coefficients to be the proper sign. If they're not, we have an issue and we need to correct it. Ideally, the coefficients should all be significant, and therefore the t-statistics should be at 0.99 or above. Errors should not be patterned or autocorrelated, as the slide says. There are a couple of things we look at. One is the Young box statistic, and the other is the error autocorrelation function. Okay, and that's really how we go about this. Now, before we summarize and close up the webinar, I'm actually going to show you one more example. And this example, data is slightly different than before. I'm going to actually change the graph and just point out I've got a data set here. This is the one we've been working with before, which I've labeled here Eastern. But I also have some other series. I've got the Midwest, which is a different series. I have the Pacific region, which is happens to have much more of a trend than the others. But oftentimes when you're building regression, you may have variables that are very similar, and you want to build a regression model that is basically using the same terms for the different items. And that's very straightforward to do, particularly with the automatic dynamics. So what I'm going to show is, let's go into regression here. and I'm going to build a model that has heating and cooling degree days, just like we did earlier, and automatic dynamics. And when I click OK, that'll build the model. It's exactly the same model we had in the first example. But now what I'm going to do is apply that model. So I'm going to apply that model to the other items, okay? And now I've, in addition to using that model for the Eastern region, I'm also using it for the Midwest, and I'm also using it for California, for the Pacific region. So the main point here is regression does require some work. You need to experiment with the variables. You need to look at the diagnostics and make sure you've got a model that you're happy with. The work is pretty much up front, so that going forward, maintaining these models, you know, a month goes by, we update our data sets, we pick up where we left off, and usually that's all we need to do. If we have data that's very similar, then usually the models you build are going to be pretty similar, and that's also very straightforward. So again, does regression require work? Yeah, it does, but the work tends to be mostly up front, and maintaining the models and updating the models tends to be vastly simpler than building them initially. So let's summarize a little bit, and then we'll take some questions. Dynamic regression should be considered when there are important explanatory variables, and I would say particularly if you have leading indicators. In addition to simply generating a forecast, a well-specified dynamic regression model is going to give you insight into relationships between variables. So again, if price is in my model, I'm going to have some understanding of how price influences demand. It also allows me to vary those variables. So the forecasts, you know, what if we raise the price? How does that change demand? What if we lower the price? How would that change demand? What if we left it the same? So I can do what if, and that can be pretty powerful. Again, one of the downsides is it's not enough for there to be a relationship. I also need to be able to forecast the explanatory variables. And if what you're trying to forecast is harder to forecast than demand for your products, chances are you're not going to be using dynamic regression, or at least not improving upon the results you're getting from other methods. Building the model is an iterative procedure. It is, if you have some knowledge about the data, you really need some knowledge of the data, and ideally you need some experience in the model building process. It's not rocket science, it's not extremely difficult, but it is the kind of thing that the more you do it, the easier it gets, and the quicker you start to recognize conditions and build models appropriately. Okay, so that's our summary. I'm going to say a couple little things about the software that we've been using and some services that are available, and then we'll open it up for questions. The software we've used throughout the webinar is Forecast Pro. If you are familiar with Forecast Pro, or let's do it the other way, if you're not familiar with Forecast Pro and you'd like to learn more about the software, we'd love to show it to you and to answer any questions you have. One of the easiest ways to do this, or the most effective ways to do this, is to get a live WebEx demonstration. And you can actually, if you use the chat functionality to send us a request, we can set you up with someone who will lead you through the software and even use your own data if you want. There's a lot of information on both software and on forecasting on forecastpro.com. We'd encourage you to visit that website. And if you do have questions and want to contact somebody at either our US or UK office, the numbers are here as well. In addition to software and webinars, we do also have product training workshops. We also offer seminars. We also have a blog. It's called theforecastpro.com, and there's a lot of good information on practical applications for business forecasting. So some good resources there. Okay, so at this point we're going to open it up to questions, and for those who've been typing them in, we'll see if we get to yours or not.
Okay. Thank you, Eric and Sarah. We'll jump right into it. I'm going to read this one pretty much ad verbatim. Can you speak to collinearity between variables? I have heard practitioners say, don't worry about it as long as it makes sense and works, whereas researchers are very opposed to including variables that are collinear.
Okay. I think I'll take that if that's okay.
Oh, yeah, go right ahead.
Okay. Collinearity, first of all, what is it? And it's basically if you put two variables that are highly correlated with each other in the regression, that it can basically make the model unstable. Every textbook on regression will have a great deal of coverage. I agree with the person who posed this question, which is in academic circles, they seem to make a very large deal about collinearity and the dangers of it. In practice, what tends to happen is that if you have two variables that are collinear, both of them will become insignificant. And what I said before about when you make changes to the model, only change one thing at a time. Once you take one of those variables out of the model then basically the collinearity is gone, and the other one pops right back in if it's important. So I actually agree with the person posing the question, which is it is a theoretical, theoretically it's a big problem. In practice, it's easy to spot and easy to correct. You want to add anything to that?
The only thing I would add to that is, I think there is a question of how collinear. So I would say that if you have moderate collinearity and you have both variables in the model and they are both significant and make sense, that even if your correlation coefficient is relatively high, it's okay to keep them both in the model if they both make sense and are significant.
Okay, moving on to another question. If you are forecasting for many products, especially in some kind of hierarchy, can you run a dynamic regression at an aggregate level, like say a category, and then proportionally allocated down?
Yes, that's very simple. Yeah, so top-down forecasting would work the same as it does here, so that if you have a dynamic regression model applied, the functionality will be identical to the previous functionality in terms of the allocation.
Yeah, I would just add to that briefly. Understanding and being able to quantify the relationships between variables often requires volume. And so what's described here, which is we build a regression model at a high level of aggregation or at a group level, and then use a top-down approach to push that down. That's actually reasonably common, and I think a pretty good practice. Because at a higher level, you've got more volume, more structure, and it tends to be able to support regression models better than, say, a SKU level or a customer level forecast. So I've definitely seen people who build regression models at high levels, time series models at lower levels, and then use a top-down to allocate downwards. And I think if the circumstances warrant it, that's an excellent practice.
All right, I think we have time for one more. Once again, if we didn't get to yours, we'll email you. But this one has been posed in different ways a couple times. I mean, it's a little bit more specific to the Forecast Pro software. Well, I guess I'll just phrase it myself since we've gotten a couple different phrasings. The variables that we use today, did we have predictors for those, or is the system running time series analysis on them to create predictors for them? Yeah. Would that be a feasible approach?
That is also a very good question, and quite honestly, after I went through some of the variables, we were looking at cooling 66, I realized I didn't mention the new functionality that we have, so the answer to that is yes. If you do not provide forecast for your explanatory variables, there is an option for having Forecast Pro use expert selection to generate forecasts for the forecast period. And that often is going to make sense for some variables. If you do have internal variables that really are planned for, I don't think I would recommend that at all. It's a much better idea to actually put in what you have the idea that you have whatever marketing plan you might have. But for some of these external variables where it's a lot more difficult, that is an option and probably a good option.
So that was the other part of the question. Is it good practice to do so?
So let me address that as well. But Sarah has addressed it pretty well as well. Okay, so there is a question of what if I simply use expert selection or exponential smoothing or Box-Jenkins to extrapolate all of the explanatory variables and then use regression. And you can actually mathematically show that if you extrapolate all of your independent variables using time series methods and then build a regression, that you're basically just building a time series model, okay? So I don't think a best practice is to use time series to forecast all of your variables. But notice I keep emphasizing all, because what's pretty common is, you know, I've got 4 variables that go into the model. There are a couple of them that maybe are internal variables, they're under my control, I have a reasonable scenario for what they'll be in the future. So maybe that's pricing, maybe it's a promotional schedule. But I also have other variables there which I don't have control over. And so in those cases, I think there can be real value to using the forecast that you've come up with for the internal variables, and then just letting using a time series method to extrapolate the other ones. So again, a bit of a more, you know, nuanced answer, but yes, it is functionality that's supported in this particular software and in others. And I think those mixed models where some of them you're supplying forecast, other ones you're automatically extrapolating, can be quite powerful. Okay, so that brings us to the end of our hour, and I want to thank everyone for taking that hour out of your day and joining us for the webinar. I hope it's been useful. I hope you've picked up a tip or two. We will be, this is a quarterly webinar series, and we will be emailing you about our next webinar once it's been scheduled, but it'll be about 3 months from now. And just to remind you, as Eric mentioned, on forecastpro.com, we also have an archive of all of our previous webinars, and I would encourage you to explore those as well. So thank you once again, and hopefully we'll see you next time.